Okay, then I suggest we get started. So first of all, good afternoon to all of you. My name is Erik Delaru from the University of Leuven and Energieville in Belgium. And it's my pleasure to welcome you to this SpineOpt webinar. Now, before diving into the actual topic of today's webinar, given that this is the first webinar in a series of four, I would like to first provide a bit of context and say a few words on the overall SPINE project as a whole. So I assume that most people attending this webinar are familiar with models being used in the energy sector, but it might be good to reflect for just 1 minute again on why we develop and use such models. As we all know, our energy system is in a continuous transition and in an aim towards strong decarbonization. Drastic changes are currently taking place. And apart from these transition dynamics, our energy system is complex with lots of interactions and feedbacks. And it's therefore, let's say, not straightforward to anticipate effects or impacts of certain decisions or changes. And also, obviously, doing experiments in this case is not really an option. And that is why we often resort to models in this domain to get insights, to understand the mechanisms that are at work, to observe trends, to obtain qualitative and or quantitative outcomes. And then just to go a bit deeper in some of the trends in the energy sector and the connection to models. So we have an energy system that needs to become carbon neutral. So we face an increasing share of renewables and a more integrated energy systems with increased levels of electrification, stronger interactions between different energy vectors, and the consumer to take up a more central and active role. And next to these evolutions in the energy system, we have corresponding challenges for models. And that, first of all, need to be able to deal with these integrated energy systems. Then second, we here also see an effort towards model consolidation, increasing the transparency of the models, the reproducibility, and facilitating access to data. And then lastly, also having efficient approaches to easily adapt models to the right setup, linked to the question that we want to address, to have the right scope and resolution in our model, to be able to work with certain data sets, etc. So there is need for developing computationally efficient models so that we can solve problems at the relevant scale. And that is then where, let's say, the SPINE project comes in. So SPINE stands for Open Source Toolbox for Modeling Integrated Energy Systems. So SPINE is a project funded under the EU's Horizon 2020 program. And in the consortium, we are with 5 partners. So we have VTT Finland as the coordinator. We have KTH in Sweden. We have KU Leuven in Belgium, and UCD and Energy Reform both from Ireland. This project has been running for 4 years, and it's now in the final phase of the project. And the overall aim of the project has been to build open source tools to help modelers manage data and workflows for models working at various scales across energy systems, and to also build a flexible open source model for integrated energy systems, and which is in fact SpineOpt and the topic of today's webinar, and then to showcase these tools and model via a number of case studies. And here you see the series of webinars that we are organizing. So today is the first one on SpineOpt, which is the new open source Julia-based energy system modeling framework with a strong focus on adaptability of the model, on the temporal resolution and representation, and on system integration. This webinar today is in collaboration with the ERA Joint Program on Energy Systems Integration, where a number of the project partners, including myself, are also active in. Then tomorrow's webinar will be on SPINE Toolbox. SPINE Toolbox is the open source software that was developed to manage data, scenarios, workflows for modeling and simulation, We will also have some examples here of how Spine Toolbox is used in other projects. And this webinar will be in collaboration with GPST, the Global Power System Transformation Consortium. Then on Thursday, we have the webinar on the case studies. So here the Spine tools will be demonstrated through 6 selected case studies, covering, amongst others, sector coupling, co-optimization of operation and investment, stochastic modeling, and rolling horizon optimization. And here we'll also have several live demonstrations. And then finally, on Friday, we have the webinar on Spine interface. So where Spine Toolbox is the open source data and workflow management tool that works with models written in any language. Spine interface is a Julia package that links the data management capabilities of Spine Toolbox with the Julia Jump modeling environment in a very direct way, which then also allows to simplify the process of developing optimization models. Via the link below here on the slide, you can still register for these webinars. All webinars will also be recorded and made available via the Spine website. And then before we dive into the actual matter of today, briefly some housekeeping for this webinar. So as I said before, this webinar is being recorded. So at this moment, we have turned off all your webcams and also muted your microphones. So regarding the questions, we propose that these can be raised during the presentations by using the chat. And then dependent on the question, we might answer that question already in the chat or come back to it later during the Q&A. At the end of this session, we'll also have a Q&A. There we propose that we use the raise your hand system that we have available here in Teams, and then we will unmute you to raise your question, or alternatively there you can also still use the chat to raise your question. Then as presenters for this webinar, I'm very pleased to now introduce Maren Illeman from KU Leuven, Topi Rascu from VTT, and Jody Dillon from Energy Reform. So with that, I would like to pass on the floor to Maren. Maren, the floor is yours.
Thanks so much, Eric. I'll quickly share my screen as well. I hope slideshow. That's perfect. I hope you will be able to see my screen. Oops, that's yes. Okay, perfect. So warm welcome also from me. Thanks, Eric, again for the introduction. I'm Maren Illeman. I'm doing a PhD at KU Leuven, and I have the utmost pleasure to present SpineOpt to you, a flexible energy system modeling framework in Julia, together with Topi and Jody. And before we dive into things, quickly having a look at the agenda. What do we have in mind for today? So today is a bit giving you a feeling of how to SpineOpt and what are the particular core aspects of SpineOpt. I will start out with a short motivation, pretty much in line with what Eric has said before. Then I will look with you guys into the basics of SpineOpt. We will have a look at the fundamental building blocks of a SpineOpt model, which then sets the floor for a presentation on the flexible temporal structure by Topi Rascu. And after a short break, he will also take you through the flexible stochastic structure, followed by Jody Dillon on the representation of different energy sectors with SpineOpt and how we're trying to tackle model complexity and details. And after that, we hopefully still have time for lots of your questions, and hopefully we can answer them to your satisfaction. So let's dive into things. As I said before, first the motivation. Why do we actually need new energy system models? Or you could reformulate this, why have the requirements for energy system models changed? And that is simple because, well, the answer to this is the energy system models are transitioning, are changing. And one of the factors that we're seeing is, of course, that we have more variable renewable energy sources. And those come with some challenges, for example, that we have more uncertainties and that we need to consider more short-term detail in our long-term planning models. At the same time, we want to look into the interactions across different energy sectors. So, for example, how do these uncertainties predominantly in the power system influence, let's say, the gas system, or also how do other energy sectors provide flexibilities to compensate for those effects? And this in turn means that we need to foster more collaboration. So different people need to come together. They need to find a common language to talk to each other. And last but not least, we see that this slide is becoming more and more filled, more complex. And this is also what happens in our models. They are becoming more and more complex, and we somehow need to tackle this complexity, making sure that our models are still tractable. And this leads us to the key features of SpineOpt. So in SpineOpt, we have tried to tackle these challenges on the one hand with a generic concept. So we tried to formulate this in a generic data structure way, making it possible for people from different fields to come together. We have tried to enable the user with a flexible temporal and stochastic structure, giving all the flexibility to account for those uncertainties and those short-term details in long-term planning models, while trying to tame this complexity by enabling the linking of models and also decomposition techniques. Another key feature of SpineOpt is the multi-sector modeling and the wide range of applications that we are supplying. On the one hand, we can model detailed unit commitment problems, but at the same time, SpineOpt also enables long-term planning models. We have case studies on hydro scheduling, heat system optimization, gas network optimization, and so forth. And last but not least, another cornerstone is our open source character. So SpineOpt, the backend, the mathematical formulation of the energy system modeling is in Julia, while our front end, the Spine toolbox, where we enter data, where we interact with different tools, is in Python. And last but not least, of course, our development happens in GitHub. And that's also where I very quickly want to emphasize these two links. The first link is just our GitHub repository itself. And the second link would be where the documentation of SpineOpt is hosted. So feel free to go look there for maybe more information on SpineOpt if you still have questions after this webinar. Great, so let's have a look at SpineOpt itself. And before we can look at SpineOpt itself, we have to look at the SpineOpt family. How does the Spine project work together, the different elements? And that's illustrated here. So to the left-hand side, we have an illustration of the Spine toolbox, which is our skeleton for workflow management. So what we can do here is we can manipulate data, we can import data, we can export data. We have a graphical user interface that visualizes our data, and we can execute tools. Basically, this is where the user can organize his workflow. Of course, Spine Toolbox is implemented in Python, which is not necessarily always the language that our models are implemented in. Oh, one thing I've forgotten, of course, if you are interested in the Toolbox, please stay tuned tomorrow for the webinar on Toolbox, where you will explore more on this front. For the interfaces, on the other hand, to come in as a connection between the models and the Toolbox, we have, amongst other interfaces, a Julia Python interface, Spine interface, which also has a designated webinar on Friday, where we will explore how easily we can set up new energy system models with this interface. And last but not least, SpineOpt that we're looking at today, which also has a follow-up webinar on Thursday, where we look at the different case studies that we have implemented with this tool. So today, building structure of SpineOpt and what are the specific characters of SpineOpt, and that's what we're going to dive in right now. And I'm going to set the floor with SpineOpt's building blocks. And first of all, we can distinguish ourselves between two different kinds of building blocks that SpineOpt encompasses. On the one hand, the model object classes, and I'm sorry that this symbol is popping up here. Yes, and on the other hand, the system object classes. object classes, model object classes, those refer to, let's say, the core optimization model. That means something like how long am I optimizing, which algorithms, which resolutions, and so forth. So really optimization related, while the system object classes correspond to our physical energy system. And in practice, this means that we have a model object that holds general information about the optimization problem in hand, the model start, model end, which algorithm am I using? So core elements. Then on the other hand, we have the temporal blocks that define the model's temporal resolutions. And particular emphasis is here on the possible plural of resolutions, because the temporal blocks actually allow us to have different resolutions in different parts of the model. So let's say a region, one region might have other temporal resolution than another region. And the same flexible concept is also realized with the stochastic structure. So the stochastic structure does the same for how the stochastic scenarios are present in different parts of our model. So again, a different region can have a different stochastic structure. This allows us high flexibility, but I don't want to go too much into detail because Topi Rasku is going to dive into detail here with you later. On the other hand, we have the system components. We try to refrain to really generic names so that they're speaking to people from different fields. And the core element that we have here is the node. That's basically the place where the energy balance happens. So where different flows are coming together. And this can represent a bus, a region, a country, whatsoever, basically just flows coming together. Then next to the node, we have the commodities, which is optional. This just allows the user to assign a specific tradable good to a specific energy flow. Those are, let's say, the more static classes, while we also have the more active ones that enable that something is happening, which is on the one hand, the connection that represents a transport process between two or more nodes. And on the other hand, the unit that represents an arbitrary conversion process to and from nodes. So a connection can typically be something like a gas pipeline or an electricity line, while a unit is probably a typical example would be a power plant or a chemical separation process. And so far we have looked at those kind of disentangled, but we need to make sure that they can actually interact with each other. And for that purpose in SpineOpt, we're using relationships. So with these gray lines, we're indicating, for example, that a unit is somehow connected to a node, allowing an energy flow to happen from or to a node. And the important thing to note here is that we're not just having relationships between system object classes, but also between system object classes and model object classes, allowing us, as said before, for example, a node to have a specific resolution associated with a temporal block. To fill all these things now with information, we're using parameters. For example, just exemplary, some spotted here. For example, a model start, which is a daytime parameter, a temporal resolution of 1 hour. A node might have actually a storage state variable, so we can assign a Boolean parameter to this, or a unit might actually represent a clustered unit commitment, so we can assign a number of units of free to this. Great, so now we know how SpineOpt works, right? But maybe not quite, because this might all sound quite abstract to someone who has never seen SpineOpt before. And that's why we have decided to walk through a small live demo with you guys to kind of give you a grasp of how to SpineOpt. So in the next 10 minutes, 10, 15 minutes plus minus, we will walk through this live demo here of this very basic energy system model. What we have here is a gas plant that is gas fired and provides electricity to an electricity node. This electricity node in this example has a varying demand over time. And what we see below is that we apparently also have some renewables. So we have 3 wind turbines with a specific availability and some capacity constraints, of course, so that they can not just ultimately provide as much capacity as they want. And yeah, so let's see how this could be realized in SpineOpt. So I'm going to quickly exit this presentation. I hope you can still see my screen, but unless someone shouts, I will assume this is the case. And we This is our blank Spine Toolbox project, and I will first start out with a data store where we're going to store our data for this particular example. I'm going to select an SQLite format for this, and we're going to create a new Spine database. Save this, and yeah, we're going to override this. I've done this tutorial more than once, so we will have to make sure that we're starting from a blank project. And what I wanted to add as a disclaimer here is that I'm not going to into every detail of Spine Toolbox, but tomorrow the guys of Toolbox will take you by the hand a bit more. So this is kind of a teaser, let's say, for how to use the toolbox as well. And if we're looking at this data store, we do see it's indeed quite empty. So let's change that. And the first thing we will do is we will select a tool which is called Load Template. It's a tool specifically for SpineOpt. And this tool allows us to import the skeleton of SpineOpt. So all these object classes that we had seen before will be imported to this particular data store, so we don't have to start from zero. So we'll quickly make sure that this is an actual output to this tool. And if we execute this now and open our data store again, we will see, aha, indeed, object classes that we had seen before. But as these are all basically grayish, we see, okay, there is no instances of these object classes yet. So to give ourselves a little bit of a head start, we will import a template for a very simple model. And this is actually online on GitHub, so you will be able to find this template if you go to the SpineOpt repository, go to templates and models, and select the basic model template. And if we open that, we see indeed something has happened. And among these things, we have now a very simple model object that is connected to a temporal block and a stochastic structure. And this can serve us as kind of like a backbone to our energy system model that we want to build. However, we still need to define a model start and a model end. So we're going to add these two parameters right away. We're going to select an alternative name. And in this case, we are taking it slow. So we will just take one alternative for each parameter. So we will just have one option for the realization of every parameter for now. And typically a model start is a date time. And in this particular case, we're going to select the 1st of January. And when we looked at our previous example of our energy system model, we saw that the model start was somehow 5 hours before the model end. So I'm just going to select a model end that is 5 hours after the model start. Perfect. And what we also want to do is we want to optimize this for every hour in these 5 hours. So we're going to select a resolution of 1 hour. How do we do that? We go to our temporal block and change the resolution, which was originally 1 day. And we're going to change this to 1 hour. Perfect. And that's it. So now we can jump to the physical system, and we're this with 2 nodes. One of them is called electricity, and the other one we're going to call gas. And at the same time, we also want to make sure that we have our power plants ready. So we're going to add a gas plant and some a wind farm. And as I said before, to make that these guys are actually talking to each other, they're coming into interaction, we're going to select some relationships between those. So we're going to define a unit from node relationship between the gas plant and the gas node, which means that this unit can draw from the gas node. Perfect. And at the same time, we're going to define another relationship, a unit to node relationship between the gas plant and the electricity node, which means that the gas plant can now provide electricity to the electricity node. And the same relationship we're going to define for the wind farm to the electricity node. Perfect. So that means that our physical system sort of looks like our previous example. But of course, we still need to fill this with the specific unit characteristics. and the different parameters that we had predefined. So first of all, if we jump back to our energy system, we might want to make sure that the demand for the electricity is actually time varying. How do we do that? We go to our node objects, to our electricity node to be precise, and select the parameter demand. Again, we're only looking at the base alternative, and we're going to select a time series which has a fixed resolution, and we're going to add the data that we had seen before. I quickly just copied and pasted it here just to be a bit faster today. Perfect. And we had another time series. When we look at the wind turbines, they had a specific availability that was typically below 1. I'm also going to copy this and add this for our wind farms. So I'm going to select our wind farms. I'm going to the object parameters of this, and I'm going to select that the unit availability factor, please be time varying by editing this parameter value, selecting a time series of fixed resolution. And here we go, I have this beautiful profile. Now we're already a bit closer. We still need to make sure that wind farms are actually 3 of a kind. So we want to make sure that there is a number of units that is equal to 3. It just means that we will have 3 units of that kind that are of the same characteristics. Those ones are supposed to be 3. And also making sure that these 2 units cannot produce ultimate capacity. So we're going to select a, whoops, sorry, almost there. We're going to define a unit capacity for the gas plant to the electricity node, which we set to 40. And the same thing, we want to make sure for the wind farm that each of these wind turbines in this wind farm only has a capacity of 20. Perfect. Almost there. Now let's see what we have forgotten. We still need to make sure that we cannot buy gas completely for free, and that we have an efficiency of 40 for this gas plant. So let's quickly jump back. Unit from node. So the relationship between, so I'm going to associate a fuel cost with the stream from the gas to the gas plant. I'm going to select this particular relationship. I'm going to assign a fuel cost of 4 megawatt euros. I think 5 euros per megawatt hour. And now only the efficiency is missing. And this one is slightly tricky, but we can manage. As I said before, we have a unit from node, unit to node relationship, so we could be happy. However, in SpineOpt, it's possible to have multiple outputs to a unit or multiple inputs. So to make sure that this relationship is unambiguous, we're going to define a 3-way relationship between a unit, node, and a node. And that means that we will have a relationship between the electricity and the gas plant, the electricity, and the gas node. And for this entity, we're going to define the parameter fixed ratio out in, which just defines that there is a fixed relationship between the outgoing and the incoming unit flows. Perfect. Almost there, but as I said before in my presentation, the node is always the place where a relationship happens. However, if we're thinking about our gas node, this one is actually only delivering energy flows to the gas plant, but there's no input. So to make sure that our system remains feasible, we will define that the balance type for this one is balance type none, which just means that this one can either work as a source or a sink. So we're just going to neglect the energy balance for this particular instance. Now I'm quickly going to save my process. And we're done. We have our energy system. Well, not quite, because we have not executed it yet. So to quickly do that as well, I'm going to drag my Run SpineOpt tool here, and I'm going to create another data store just to store my outputs. I'm going to make sure that this one is actually empty so that we're not seeing any old results. And I'm going to make sure that my run SpineOpt tool has the right inputs and outputs. And now I'm going to execute this, and hopefully I have not forgotten anything. We see something that we do have an infeasibility, so probably I did forget something. So if I'm quickly going to jump back to my database, I hope I will find the error immediately, because I've been talking too much here. God. This is, of course, what always happens when you're doing a live demo. I'm gonna. God, how did I end up not doing this correctly? Can't believe it. I have done this demo so many times that this is, of course, inevitable. I'm just going to quickly give the scepter already to Topi Vasco, and he will probably show you the outcome of this demonstration, and I will quickly see what went wrong here in my presentation. I'm very sorry about this, but Topi, the stage is yours.
Okay, so hello everyone. Hopefully you can see at least me at the moment. And yes, Maren, I have your results on my on my end, so I can show what should have happened. But yeah, let me quickly share my screen as well. So you should be seeing my screen. I hope someone can quickly confirm that, so that I don't launch into anything.
Yes, we can.
Okay, thank you, Nelly. But okay, so yeah, hello everyone. My name is Topi Rasku. I'm from VTT, and I'll be giving you a brief presentation about the basic ideas behind the flexible temporal structure, as well as the flexible stochastic structure. But we'll take a little break in between, just to sort of give you an opportunity to take a breather. So, okay. First off, a bit of reminder, a gentle reminder why we think this is important. Well, as Maren already mentioned, when you're doing models where you integrate different energy sectors, it gets a bit difficult because traditionally all these different energy sectors have been operated or modeled on a slightly different scales. So for energy systems or power systems, in this case, the energy markets typically operated in hourly resolutions, moving towards 15 minutes in the future. However, some reserve markets might already operate on the minute scale, or if you're concerned about power system stuff, you might have to go to second or millisecond scales. However, when you're modeling, for example, district heating systems or building stuff in general, or gas grids, the minute scale might not really be relevant. So you might be wanting to look at hourly or multi-hourly or maybe even daily scales, depending on your applications. And then on the complete far side, you have these large-scale hydropower reservoirs or other large-scale energy storages. And when you're scheduling those, your model might be running on daily or even weekly, maybe even monthly resolution or monthly time steps if you're doing really, really long-term energy system or energy storage scheduling. But yeah, the basic idea behind the flexible temporal structure in SpineOpt is that, well, we wanted to make a temporal structure that supports different time resolutions in different parts of the system specifically for this reason. And as Maren already showed you, it is, in principle, it is a very simple sort of building block. We have this object called temporal block, which essentially is just a period of time which has a defined start, end, and time resolution. And these temporal blocks are then connected to different nodes or units in the model to define how time works in those parts. And just this simple sort of option gives you a surprising amount of flexibility, which I think Jody will be showcasing a bit. But the main motivation here is that we want to put the resolution only where it counts. Because when you're having a large model with all sorts of energy systems, you don't really want to model your large-scale hydropower reservoirs with 15-meter resolutions. You'll just end up with a whole bunch of variables and constraints that don't really need to be there. So, as I promised, I'll show you the modern result, but along the way, I'll also give you a bit of try to make it a bit more concrete to sort of show you what it is I've been talking about. So basically, I'll be working on Maren's previous example, and I'll be messing with it. So what I'll be doing is that I have this new temporal block that I'll be adding into the model, which has a different resolution than what Maren used in her model. And I'll be connecting it to only a certain part of the model. Actually, you probably can't see that pretty. So yeah, which in this case is the gas node. And then I'm going to run the model again and see that at which or what changes. So if I'm going to be switching here, I hope you should now be seeing the toolbox again. And this is the same project that Maren was showing you previously. So before I get into the details, I'm quickly going to show you what the output looks like. So this is not quite as colorful as the input data, but in any case, the most interesting results from Maren's example are probably here in unit node direction. And from here, we have different time series for different outputs. For instance, here we have the electricity output of the gas plant. And if I double click here, I get to see, okay, here we have some time series. But what I can also do is I can just take them all and plot them here. So this plotting is not perfect, but it's nice for preliminary stuff. But from here, we can see that, okay, the model is doing something. We have this orange line, which is the gas input, which is higher than the gas plant output. And then we have the wind farm producing some electricity. So everything in this case is working as it should.
And if I may mention one thing, I can also quickly show what the problem was, because if you're clicking at the gas 2 nodes unit flow, this one actually goes up to 44. And in my nervousness, I added the unit capacity at 40 megawatts instead of 50 megawatts. And that's why we got an infeasible system. Sorry about that, but problem solved. Please, Topi, continue. Sorry for the interruption.
Okay, thanks, Maren. But yeah, so what I'll be doing now is I'll be messing with these results and showing you what this flexibility in our temporal structure sort of means in practice. So first off, I'll show these temporal block objects. This is our input database now. So this is the place where Maren just showed you how she built the system. But here in the temporal block section, we have the different temporal blocks in our model. This is the flat temporal block. And if I select this, whoops, I'll quickly change this look to be less confusing, hopefully. But basically here we have the flat temporal block, which has a resolution of 1 hour. So Maren's model was working on a 1 hour resolution. And here we can see that, oh, this temporal block has been set as the model default. And what this means is that this temporal block is used everywhere when there is no other definitions. So this is for convenience. However, what I've defined here is this flat 2H temporal block. And the only difference between this temporal block and this one is that now I have a time resolution of 2 hours. So this is a coarser temporal block. And what I'm going to do here is I'm going to add this temporal block to the simple model. So now the model knows that this is a valid temporal block. And then I'm going to connect this temporal block to the gas node. So now our gas node is actually using a 2 hour time resolution. instead of the 1 hour that the rest of the model is using. So now that I've saved my changes to the input database, I'm going to execute this model again. And I'm fairly certain this should now work, because I didn't just create this from scratch. And yes, looks like we have some stuff. So this might look a bit intimidating, so I'll be just focusing on the important parts. So first off, now what we have is we have two different results for the electricity output to node. And the difference is that the database saves results from different times in different timestamps. So I have the results previously and I have the results from just now. And if I plot the electricity output from the run I just did and the previous run, you see that there's actually no change. And this is because the electricity node is still working on 1 hour resolution. So the electricity output from the gas plant is on an hourly resolution and there is no change. However, if I plot the gas input into the gas plant, now we can see that, oh, there is a change. And the change is that in the previous run where we had an hourly resolution also on the gas node, we see this hourly profile identical to the electricity demand. However, now that our gas node operates on a 2 hour time step, we get these. And this is coarser. And the way the energy conversion ratio constraint works is it deals in average energy, basically. So the output is still able to produce this type of curve, even though the input looks like this, because the input sort of only requires this average electricity or average gas demand to match. So yeah, that was basically a very brief example of what SpineOpt is capable of and should be used very carefully because you can do a lot of things, but that's not necessarily always a good thing. But yeah, in any case, at this point, I believe we are scheduled for a quick break. So take 5 minutes. I guess we'll be back at what's the CEST in 5 minutes anyway. It's a minute to whatever, minute to 2, I believe, in Central European summertime. So yeah, see you in 5 minutes. Okay, I believe our 5 minutes are roughly up. I hope you had a nice breather because things are still going to be very flexible after the break. So I'll just hop right back onto it. You should still be seeing my screen and hearing my voice, I hope. Thanks, Eric. Okay, so next up, I'll be giving you a very similar demonstration about the stochastic structure that we have in place as what the previous stuff about the temporal structure was. So yeah, starting with, again, a gentle reminder why we're going to the lengths that we're going. So yeah, the primary reason why we're concerned with stochastics in the first place is that variable renewable energy generation is starting to be kind of a big deal. And since it's variable, you don't really know ahead of time what you're going to be getting. So representing that uncertainty in your models is kind of important. Again, however, when you're dealing with multiple different energy sectors you're trying to integrate and squeeze into a single model, you run into issues with that. Okay, even though my wind and solar electricity generation is uncertain and I need to have stochastic scenarios, other parts of my model like district heating demand or hydropower inflows or stuff like that, you might not necessarily have meaningful stochastic data for it, or you might just want to make some modeling choices that you want to keep those things the same regardless of what your variable renewable energy generation might be in different scenarios. So again, the basic idea in the stochastic structure of SpineOpt is very simple. We have this stochastic structure object, which essentially is just a handle for a number of stochastic scenario objects, which form your desired scenario tree. And again, when you have this rather simple object, the flexibility comes in the possibility of connect these stochastic structures to different parts of your model, like nodes and units, to define how stochastics are treated in those parts of the model. And again, the motivation behind this is that you really want to be able to focus, or we wanted to be able to focus the stochastics where they count, because, well, again, having 5 different stochastic scenarios for every variable and every constraint in your model might be overkill just because you want to model wind power or solar power variability. You might want to focus them only where you want to. So again, the plan is the same. I thought I'll show you a quick demo about what happens when I mess with the system I had previously a little further by adding a new stochastic structure into a part of the model and running the results and showing you highlighting some changes of what actually happens. And the plan is to add this, or have this guy called simple tree, which has 3 forecasts about the future with different data, as well as the sort of what comes before it, the realization part, and connect it to both the electricity and gas nodes in this case. So now you should be seeing the Spine toolbox again, and I'll be opening the input database again. And the first thing I want to show you is that, unlike in Maren's example, where the electricity demand was a time series, this time we actually have a map. And what a map is, it's basically just an indexed container. And here I have the different stochastic scenarios in my model mapped to different time series. And I can actually plot this, so I can show you that, okay, we have different electricity demand for different scenarios. The blue line for the realization scenario is the one we've been using so far, but now we also have different electricity demand for forecast 1, 2, and 3, respectively. And as you can see, they're all slightly different. As for the stochastic scenarios, these are all objects. However, these are basically just labels for different scenarios you want to include in your structures. Like, they don't hold any meaningful parameters by themselves. Where the magic happens is in these stochastic structure objects. And first, I'm going to quickly show you this deterministic object, which is the stochastic structure we've been using so far. Again, it has been set as the model default. So this stochastic structure is used everywhere in the model unless otherwise specified. And if we look at this stochastic structure, stochastic scenario relationship, it only includes the realization. So this is a very simple stochastic structure. It only has one stochastic scenario. Basically, it's just, as the name implies, it's just a deterministic stochastic structure. However, what I have for the simple tree is slightly more complicated. So for this simple tree stochastic structure, I have 4 stochastic scenarios linked to this stochastic structure. I have the realization and I have all the forecasts. And for this, I'm going to quickly change the view in the toolbox to give you a better look at what actually makes this stochastic structure. Here we can see the different parameters set for the simple tree. So the first thing we notice is that, okay, for the realization scenario, we have this parameter stochastic scenario end set at 2 hours. And what this means is that after 2 hours of model time, the realization scenario ends and it spawns its children. In this case, the forecasts 1, 2, and 3. These relationships are governed by another relationship class here, which is rather simple, but for some cases complicated cases can get pretty complicated. So, but any case, this parameter sets that the realization ends after 2 hours and it spawns these. And this weight parameter essentially just allows us to assign values on how these different scenarios are weight in the objective function. And here you can see the realization has a weight of 1. So it's everything that exists unscaled. As for the forecasts, they have roughly 1/3. So they are basically probabilities for these different forecasts. So what I'm going to do now is, as with the temporal blocks, I'm just going to add this simple tree stochastic structure to the model. So the model knows it's a valid structure, and connect it to, in this case, both the gas and the electricity nodes. And basically the reason for that is I could add it only to either of them, but because there's still the input-output ratio constraint, it would make the results so that they don't really show any difference. So now that I've added that structure, hopefully correctly, I can execute the model again. Okay, brilliant. What did I do wrong? Okay, haven't seen an error like that before. So hope you'll just excuse me, and I'll do some. I have a pre-prepared input database, which should, let's see now. Can I open this? Okay, I can. I have the stochastic structure. I have the simple tree. It is connected to the model. It's connected to the nodes. Okay, let's try this again. Okay, I'm sorry, I don't know. Apparently I did something wrong there, but I have no idea what I did. However, I should be able to show you what changed. So there's a lot of output here, And in this case, when I check this, it's still a lot of output here. So I'm going to filter out everything except the latest results. So now what we can see is that for the output from the gas plant, the electricity output, we now have results for all of these stochastic scenarios. And if I plot these all, this is going to look a bit wonky because the plotting isn't perfect. But we can see that for the first 2 hours, we have results for the realization scenario, as we should. And after 2 hours, the stochastic scenarios branch out, and we have 3 different outputs for the 3 different scenarios, just like we planned. However, as a constraint, or as a sort of for contrast, if I show you what the unit online variable looks like, it only has 1 realization scenario, and this variable is common between all the scenarios. So I hope that was at least somewhat helpful. I believe I'm basically out of time at this point, so if you have any questions, please ask them in chat. Other than that, I'm going to give the floor to Jody to explain some of the more fancy use cases. So Jody, take it away.
Thank you very much, Topi. So let me find my presentation. So it seems to be just uploading now. So I'll just introduce myself while those slides upload. So yeah, my name is Jody Dillon with Energy Reform. So it's a really great pleasure to present to you what we've been working on the past 4 years. And really, having been around a while and spending most of my career working in this area of power system and energy system modeling, it's quite exciting because I really believe we've developed a tool that as modelers is the tool that we want to use, having kind of foreseen the challenges and limitations of what's been available to date. So I'm going to be talking about how in Spine we can use the different features that have been presented so far to do different things. And I don't have a live demo because I'm not as brave as Maren and Topi. So, but I think we can pack a lot more detail in. So I'll also be talking about how, okay, we can do more with Spine, but you know, how do we address some of the computational challenges? So we saw from Maren some of the fundamental building blocks of a Spine model. And so I'm just kind of zooming in on units, nodes, and connections here to show you the kind of the power of what these simple things, what we can do with them. We can implement a wide variety of systems and technologies. And so as you've seen in our models in Spine, there isn't anything that's fundamentally named electricity or hydrogen or power plant. We use a more high-level abstract data structure that allows us to model stuff very flexibly and model things that we haven't thought of yet. So it really enhances the possibilities. And while it is general, we do have many commodity-specific features so that we can also implement specific things that we'll see a little bit more about later. So just zooming in on nodes, and as Maren has said, nodes are where balance happens. Generally speaking, what goes into a node goes out, and that's its primary function. Generally speaking, they may represent commodities or services or sub-nodes within a node network. Nodes have balance, as we said, or may not. They can have storage, they can have demands, and there can be diffusion of energy between nodes to implement, for example, heat transfer. So that's what happens in nodes, and as we'll see, that there's great flexibility on how they can be used. Looking at units, as we've heard also, units are essentially where conversions happen. So it's almost the opposite to a node where what goes in comes out. Generally speaking, what goes into a unit isn't what comes out. There's a conversion, some sort of conversion. And a unit may have any number of input nodes and any number of output nodes. And we can flexibly define piecewise linear relationships between any of these. So we have simple parameters to represent relationships between nodes, flows between in and out of a unit from two nodes. Input and output nodes, or two output nodes, for example, or we can define arbitrary piecewise linear constraints that capture the relationship between multiple nodes. This gives us a lot of flexibility to implement a lot of things. So units also have an operational status that can be on or off. And we have the full range of unit commitment constraints associated with that. So we have minimum up and down times, ramp rates, shutdown and startup costs, etc., etc. And then finally, connections and connections implement, generally speaking, implement or imply some sort of transport. And by default, a simple simple transport model is used. But additionally, connections may have losses. They may have connection delays. They can be one directional or two directional, depending on how you set up the relationships. They can have capacities on any and all related flows. But also you can impose specific connection physics on connections. For example, we can impose DC load flow constraints, or N-1 security constrained unit commitment, or pressure-driven gas flows. And so when we combine all those things together, node diffusion, node storage, connections with delays or losses or specific physics, we can implement a very, very wide range of processes and systems. So just to kind of illustrate that, this goes beyond. We can even represent technologies and systems outside the energy sector. For example, we have a node here, we've called it Ocean, and it might be a node with an infinite supply of fish. A trawler that is a unit with a single input and output, and it's converting the ocean to fish. And the fish is a node with storage, and we have a connection to the fish market, which is a buoy with a basket, and that's just a connection with a delay, and the fish market is a node with a demand. So using these basic building blocks, we can do an awful lot of stuff even outside the energy sector. So just to kind of show you how this can be used in quite interesting ways with kind of energy systems integration and multi-sector modeling in mind, just taking a common technology, an open cycle gas turbine. It has one input, which is gas, but it has multiple outputs, one of which is electricity, but also might be carbon dioxide emissions, NOx emissions. This unit can provide a frequency restoration reserve, and it also provides inertia. So there's nothing built into the SpineOpt to implement these things. It's the user that defines these nodes and gives them names and gives them meaning based on the parameters and the relationships. So in this previous example, so yeah, just looking at this, we have a simple OCGT, open cycle gas turbine, just supplying energy to a single electricity node. But rather than a single electricity node, maybe there's an electricity network. So now we have multiple electricity nodes with connections in between them. And in this case, we may have PTDF-based DC load flow constraints imposed on these connections. So within SpineOpt, the solution will be feasible with respect to the properties of these connections, and the DC load flow constraints will be enforced. So we can build up networks of commodities very easily and impose specific physics. And so, for example, we have another unit in this system called coal. So it's relatively easy to define commodity networks and with specific physics. And for example, so we have electricity as part of an electricity network, and it's one node of many. Similarly, on the gas input side, maybe we want to represent the gas network, and this is again, it's the same in that it's just a network of nodes interconnected by connections, but in this case we have pressure driven gas flow constraints imposed on these connections. And so you see we have gas production units as well in the gas network. So it's very simple to implement, different networks and different commodities within Spine. So similar, we saw Maren showed how to implement a renewable unit with an availability time series. And so here's a hydro unit, for example, but maybe it's also providing reserve and inertia. And these are just nodes that have a demand that the unit must be supply, and there's a parameter that defines the relationship between the electricity output and the inertia and the frequency response reserve that this unit is supplying. But that's a simple hydro unit with an inflow time series. But maybe we want to also implement or model a cascading river system with connection delays. So maybe this water input is part of a river system with multiple storages along its length. And here the connections are representing waterways, and they're connections with delays to capture the delay in the flows. So it's very flexible what we can do. So here's just another example. So it's building on the previous example where we have gas and electricity networks implemented. But maybe we want to implement blue hydrogen, and so basically via steam methane reforming plant, we can also use the gas in this network via an SMR plant to produce hydrogen. And then maybe we have a fuel cell in the network that takes hydrogen as an input and produces electricity and reserve also. So it's very flexible what we can do. And also perhaps there's an electrolyzer in that system, and that makes the link back between the electricity, gas, and hydrogen systems. So we have a truly interconnected, integrated energy system here, where this electrolyzer is taking electricity, producing hydrogen, and also can supply reserve. And so in this system, you need to the actual production of hydrogen is just going to be a linear combination of various things. So this is the type of thing we can do. So and then just finally, by way of we can increase the complexity of specific technologies that we can model. So not just the systems, but the individual technologies can be complex. So here I have an example of compressed air energy storage, and fundamentally, case plant has two inputs. One is compressed air, and the other is stored hydrogen. And so we take in hydrogen and compressed air, and we can produce electricity, reserve, and inertia. And then via a compressor unit, we draw electricity from the grid, and we compress air, which goes into the air storage, which can be used for generation. And also via electrolysis, we consume electricity to produce hydrogen that could be used in our case plant. So this gives us a lot of flexibility in the technologies that we can model as well. So we see that we can do an awful lot with Spine. We can model an awful lot of sectors and scope, and we can also model an awful lot of detail. But just because we can build a spine model with all of these things in it, is it actually going to solve and give us interesting results? So within spine, we've addressed, that was a core part of the challenge, to address this particular issue. So we have tools, methodologies, and features to fine tune the amount of detail in our model and to incorporate more detail more efficiently. So, for example, I'll explain some of these a little bit more in subsequent slides, but we've representative days with ordering for investment problems, parallel workflow execution, which is the toolbox functionality, scenario management with automatic parallelization, that's also a toolbox functionality. So we've seen flexible rolling temporals and stochastics. I'll say a bit about that. We also have remote headless execution, where we can send modeling jobs to remote machines. And also we use decomposition to more efficiently solve co-optimized long-term and short-term issues. So representative days has been around this concept for a while. I have given a reference here about how this idea has been enhanced within SpineOpt. And so essentially what we can do is spine periods is a companion optimization model to SpineOpt. And based on the demand and renewable resource time series in a particular SpineOpt model, it identifies n representative periods that best capture the variations and the patterns of the variable resources in the model. And the user specifies what those periods are, whether they're days or weeks, or numbers of days, or whatever. That's completely open, and also the number of representative periods that they want. But that alone isn't quite sufficient for doing things like modeling long-term storage. So this is where the representative periods are ordered and weighted, but also what we do is we go through the full modeling horizon. Let's say it's a year, multiple years. Each interval within that model horizon is mapped to a particular representative day or representative period, so that for the purposes of modeling long-term storage, for example, there is a full continuous time horizon that the model can optimize across. So for example, this is an example from case study C3 that you'll see on Thursday if you attend, where we show how this is an output of hydrogen storage across the full year. And we see that the short-term operational use of hydrogen, you can see the variations from intraday variations, is co-optimized along with the long-term seasonal profile of the storage. And this is something that's very difficult to do in other tools. So we'll see in the Spine Toolbox presentation tomorrow that we can execute models or any workflow in parallel. So Toolbox will implement processes in parallel if they can be. But in particular, within a single SpineOpt model, we can use the scenario features to give data parameters many different values. Now, these are different to the scenarios Topi was talking about with stochastics. These are more like macro scenarios, like you're saying, what if, looking at different carbon prices or different investment costs. And we can specify simultaneously using alternative data different values for different parameters. And what that will do is we'll create scenarios that use different combinations of the alternative data. For example, we might like high fuel cost, low fuel cost, etc. And then Spine Toolbox will automatically run those in parallel. So it's a very efficient way to do an awful lot of modeling very efficiently. So also we have rolling optimization, which Topi showed, where you can change the resolution of different decisions. But also, for example, we couldn't solve a full year that way. The model would get too big. So a very common thing to do, it's a thing called rolling window optimization, whereas you might, in this particular example, we've just one temporal block with 24 hours of 1 hour resolution. and we solve, just say we have a year of 8,760 hours, we solve it 24 hours at a time and then roll it forwards. And so as we roll this 24-hour window forwards, our temporal structure rolls along with us in a relative way. And then these first 6 hours that, let's say, we've rolled past, the outcome, the model outcome, is then that's our retained solution that we keep. And so 6 hours at a time, we solve the full optimization horizon. So we might also, our temporal structure might, let's say, consist of a number of temporal blocks. In this particular example, we have 3. And we can see the horizon, the temporal resolution of our temporal blocks increases as the look ahead of the model increases. And this could be an efficient way to extend the look ahead of the model, but reduce the number of variables in the resulting optimization problem so that it solves more quickly, or that we can look further ahead in time. And so in this particular example, using rolling planning, this structure gets rolled forward again in a relative way. But also we've seen that different nodes might have different temporal blocks and consequently different temporal resolutions associated with them. But also unit on-off decisions, as we've seen, can have different temporal resolutions, and different units can have different on-off temporal resolutions, as you can see here. So here we've created a slightly more complex temporal structure where the temporal resolution is varying not by look ahead, but instead by node or by unit, for example. And in the same way that using rolling planning, we can solve a long period of time by rolling this forwards. In this case, let's say 6 hours at a time. So that's powerful. But if so, I'm kind of running out of time, so I'll skip through this a little bit quickly. So the nice thing is this flexibility can also then be combined with the flexible stochastics. So this is a very simple stochastic structure. Sorry, what have I done? Here we see a very simple stochastic structure, just 2 scenarios that one branches from the other, and it might be a realization scenario and a forecast scenario. But that doesn't have any temporal information or a resolution associated with it. So when we put our temporal structure together, our stochastic structure together, then we get a kind of temporal stochastic structure that's kind of represented here. And this is quite interesting. In this particular example, we have a 15-minute realization scenario, but then 1 hour resolution forecast scenario. So it's quite useful for doing this type of thing. Again, that still works with the rolling structure. So where we have this combined temporal and stochastic structure, that also can roll forward in a relative way to solve, say, a full year or a longer period of time. And so again, if we have multiple different temporal structures for different decisions, we get a different stochastic structure essentially. So for example, in this case, we're implementing an algorithm where we have a 15-minute resolution realization scenario and a 1 hour resolution forecast scenario for energy flows. And let's say that's unit dispatch, for example. But we have 1 hour resolution realization in the realization scenario for unit on-off decisions. And so that might mean, for example, that we know that, in this realization time phase of, let's say, 3 hours, we can't, make many unit on-off decisions. And so then combining all that really gives us a lot of options in terms of what kind of systems and temporal structures we can model. And that's just an example of what we can do there. And finally, decomposition allows us to co-optimize long-term and short-term problems. So the kind of traditional single-pass approach is we run a long-term model that determines our investments, and we plug that into our short-term model, and that we get our prices and our operational schedules and things like that. But the problem is a lot of stuff happens in these short-term operational models like curtailment, congestion, constraints, uncertainty, for example, that affect the value of units. And if our long-term model knew about those things, well, maybe it wouldn't have invested in them or would have invested differently because it's intrinsically part of their value. And this poses as well problems for optimization of long-term short storage. So what we do here is we use decomposition, decompose this into a master problem where investments are decided, then short-term sub-problems which determine the operations, but there's a feedback loop where the impact of the investment decisions on costs is fed back to the master problem and it updates its investment decisions, and this iterates until it solves. So what you get is co-optimization of long-term investments with short-term operations. And finally, this is a kind of specific example of how we use the multi-model infrastructure within SpineOpt. So Spine Toolbox allows us to make connections between all sorts of different models, but also SpineOpt as a multi-model, lower-level multi-model framework within Julia, where we can have multiple models alive simultaneously and pass results from one to the other. And that's how we've implemented decomposition using that multi-model framework. But perhaps in the future that can be used to do lots more interesting things, like incorporate agent-based models and that sort of thing. So apologies that I've run a little over time, and I believe we're headed into questions and answers. So thanks, Eric.
Thank you. Thank you again, Maren, Topi, Jody, for presenting and showcasing SpineOpt. So yeah, we hope we have been able to give you all a flavor of what SpineOpt is capable of, which is of course not easy to do in just 1 hour and a half. And here on the slide, I mean, it's important information. We like to really point you to the website and also the GitHub page, where you find really a lot of documentation on the model. So there's a lot of stuff to explore there. We are indeed coming close to the end, but let's at least take a bit of time still for some questions. The chat has been used while the presentations were ongoing, so that was very nice to see. I see there's still some open questions at the very end. Alternatively, as I said at the beginning, if you want to raise a question, let's say live, you can raise your hand and then we can unmute you to raise it. Alternatively, you can still use the chat to post questions you might have. So maybe also, Maren, Topi, Jody, if you want to respond, let's say orally to some of the questions in the chat, that's of course also possible. Then you don't have to.
Okay, so I've responded to the decomposition question. Let's see. We haven't implemented specific AC load flow. So we can't explicitly model voltage deviations and reactive power, but as I said, the framework is flexible, and if we want to layer, so the specific physics are layered on top of the generic structure, so it's always possible to add things, and considering it's an open project, maybe that's something the community would like to pick up. So is there something? Why is the electrolyzer connected to the coal? The electrolyzer is just connected to the electricity network. I didn't intend it to be connected specifically to the coal unit. It's just connected to an electricity node of the system. Maybe the image was a little misleading. So are there other questions you feel I should address? So how the Monte Carlo method is, and we haven't quite implemented Monte Carlo methods, but it comes down to how you construct your scenarios, and it's more stochastic programming that we're using, and stochastics, and And so you would typically need some sort of scenario reduction methodology to limit the number of scenarios you look at compared to, let's say, a Monte Carlo method. So I'm not sure if that's a useful response to that.
There's also, Jody, a question at the bottom on the short and long term. I don't know whether
yeah.
you can,
Yeah, so we've used, if you, in case study C3, we've used combined, we've used the representative periods to co-optimize long-term and short-term use of hydrogen in the Irish system. So we have that's all in the open. And you can see more about that in the case studies webinar on Thursday. We've also used decomposition to, in case study, I can't remember the number of it. Manuel maybe might, I'm not sure if he's here, but there is a case study using decomposition to optimize electricity network investments. Using PTDF-based DC load flow and security constraint unit commitment. So that's quite interesting. If that's interesting.
Yeah, thank you. Maybe because we're running against the time limit, and again, if you have further questions, don't hesitate to reach out to us. But maybe let's take the final question. Mara and Jody, Topi, whether you can see it in the chat. So what are currently the main limitations if we compare Spine to other models that are out there?
Yeah. If I was to answer that in a very short way, well, one thing that just on the reactive power thing, while we don't have AC load flow and explicit, handling of voltage, for example, anything that has a supply and demand you can model, and so, for example, reactive power could be approximated in that way, and I believe someone has used Spine to model that. The other thing, how I would characterize, in terms of, you ask why the differentiating features of Spine, I believe it's the flexibility, the amount of scope that you can include, and the methodologies and tools that we have to increase the amount of detail along with the amount of scope. So very often the traditional approaches involve a heavy kind of trade-off, and that to have more scope in terms of temporal resolution or sectors you want to model, it usually means sacrificing a lot of detail. But an objective in Spine was to increase the amount of detail that we can include in long-term models and models with a lot of scope, like using the fine-tuning the temporal structures and the decomposition approaches. So I think it's this combination of being able to include more detail and more scope at the same time that's quite differentiating. And the attention we've paid to the data aspects in the toolbox side as well.
Okay, thank you. So I would then suggest that we wrap it up here. I see there's one last favor. Okay, we'll make sure we will take care of that. So let me thank you all again. First of all, the speakers of today for their showcase they presented, and then also for the audience in participating and also raising points of discussion. So thanks to all of you. And we then obviously hope to see you again in the coming days in one of the other Spine webinars. So with that, let's finish here. Wish you all a pleasant good afternoon, and then hope to see you soon in the coming days. Bye all.
Thank you. Bye-bye.
Thank you. Bye, folks.